In this video we will look at substitution. It's a very popular method because if you get lucky, it can solve your integral with just a little bit of work. But it's also a hard method to master because it's very flexible. It can be adjusted to many different situations, so it's not possible to just provide a list of types that you would learn and then you would know, here I should use substitution. So unlike integration by parts or partial fractions, using substitution efficiently requires a lot of experience and a good understanding of what it does. So we will now explore substitution using some examples. This integral is probably the most typical example of an integral that can be solved efficiently using substitution. One way to see substitution is that it's a method which allows us to hide parts of the integral that we do not really like. And we pretend that they are not there just by giving them a nice name. In this case, I am not really unhappy about some parts here, but this logarithm is making my life difficult. So what I'm going to do, I will take logarithm and I will replace it with a nice name. Let's say y. That's traditional. Okay, here we go. Integral 1 over y squared plus 1. But now, here we come to the basic rule of substitution. The original variable must disappear entirely, and the only source for replacing it is here in this formula. Usually, it's best to start with dx. Where do I get a formula for dx? I take differentials on each side. So on the left, I get dy, and on the right, I take derivative, 1 over x times dx. And that's a formula for transforming the differential dx and changing it into dy. And I look at it and I say, wow, I'm so lucky. Dx divided by x. I can actually replace the whole group. So I do it. I replace it with dy, and I get a new integral. There should be no x's anymore, and they are not here, which is great. And now I just finished the calculation. That's a very nice integral. It's in my dictionary. I get arctangent y plus c. And now to finish it off, we do the back substitution. Arctangent, what's y? Over here. Y is logarithm x plus c. And to finish it off, we have to inquire about the validity. So we start at the beginning. Okay, there is no problem, no problem, no problem. We shouldn't divide by 0, that's one thing. And here, logarithm only accepts positive numbers. And now it should be okay. So we are not dividing by 0, definitely. The logarithm is happy. Are we dividing by 0 here? That's a good question. Logarithm is squared, so it's a non-negative number, plus 1. This is at least 1. Everything is fine. So that's a very nice example of an integral which could be solved by substitution. Now notice that the substitution didn't actually solve it by itself. It just changed it into something nicer, and that's the whole point of substitution. And this example is typical. I look at that integral and I see a part here, a component, which I would love to replace by a letter. And now, and this you can do in your head, you just take the derivative of your formula, and if you can see the derivative attached to dx, then you can rejoice because there is a very high chance that the substitution will work for you. So that's the most typical setup. You have a little component, and if you take derivative of it, you can see it next to dx. Wonderful. Just out of curiosity, a tiny change in my question. I do dx over x squared. Well, my main motivation is still the same. I want to get rid of logarithm. So y is equal to logarithm, that's my substitution. And the first fraction goes easily into 1 over y squared plus 1. And now we move to the next part. I can see dx here. So again, I take differentials to see a formula for transformation. And I can see that I can handle 1 over x dx. But there's an extra x. Well, okay, let's play with it. I can take one x away and put here dx over x. So this part can be replaced. And I put dy here. But then there is something in the middle. 1 over x. What's 1 over x? Well, This is my basic substitution formula, and I can use it to adjust. So in this case, I am really interested in, let's say, x. What's x? X is e to y, and therefore I can substitute here, and I see 1 over e to y is the right formula. Now, let's check. All the x's were accounted for, yes. No x over here, that's wonderful. And therefore, I can continue and, well, I don't really know what to do. This is a very tough integral. And you can see that I made just a tiny change, and this is typical. Substitution is a very sensitive beast, and that's what makes it tough when you are starting off to recognize confidently whether to use it or not. One has to get a lot of experience to see those little things. But anyway, by the way, one can always try to get a formula for dx, which I can get from here. In this case, it's x dy. But I cannot use it. I cannot just take dx and replace it with this expression because x would appear in my new integral. So essentially what I can do, one can get dx from here, and then from this first substitution formula, find a replacement for x, and we can write that dx is e to y dy. So I can also replace directly dx. So there are many things that I can do to somehow force the substitution through. And I did it successfully here, but then it wasn't really good for anything. Sometimes, already at this stage, you fail because you try to do a substitution and the formulas are not really so nice that you could use them efficiently to transform the substitution. So this procedure can break down at many places. It can break down here that you are not able to adjust your substitution enough. Or if you are lucky, you do adjust it enough, but then the new integral is not nice either. So there are many components that have to work really well so that at the end you get the answer. Okay, let's have a look at another example. Let's see. I can see a combination here which makes my life difficult. If this were just a single letter, let's say y, I would have 2 sine of y, and I would love it. Perhaps. We will see. So let's think about it. Such a substitution, does it have a chance? Good question. Well, I take the derivative, and it's 2x minus 4 to some power. I don't see it here next to the x. So this tells me that perhaps this substitution will not fit as nicely as in the first example. But on the other hand, I don't really see any other approach. This definitely is not a rational function, ratio of polynomials. And I don't really see here integration by parts working well. So substitution is the only option left. Can I force it? The answer is yes, but there is a little twist now. This type of substitution is called a direct substitution. You take some formula and you assign it a new name. And this direct substitution is easiest from a theoretical point of view. If you can do something by direct substitution, it saves you some trouble. However, there are 2 more types of substitution. There is something which is called indirect substitution, and it works exactly the other way. You take here x and you replace it with a formula. So the new integral will be actually more complicated. That sounds weird, doesn't it? It's used only in very specific situations. We will see soon. And then there is something which is called a mixed substitution, when you take a formula and you replace it with another formula. So you are essentially taking both approaches, putting them together. Now the indirect substitution and the mixed substitution, they are more tricky than the direct substitution because one has to worry about those formulas. Let me show you. This is a typical case that calls for a mixed substitution, at least when you have some experience, you will see it. 2x minus 4, can I replace this by a single letter? Because that would be another candidate. Perhaps this is too ambitious. Perhaps it will be safer if I use a substitution like that. It wouldn't really fix my integral, but it would make it a little bit nicer. So that's another inspiration. But what I will do here is this. I take 2x minus 4, and I don't replace it with y, but with, let's say, t cubed. And you can see the inspiration here. If 2x minus 4 is replaced with t cubed, then it cancels with the cubic root and I get just a single letter here. That would be nice. In fact, it's exactly the same substitution, but written in a different way. And now I have to start worrying. These formulas here, they should be one-to-one. I am not allowed to take formulas which are not one-to-one, and I have to worry about it. Whereas the direct substitution does not require me to worry about it. I can use any formula I feel like. So that's the main difference from theoretical point of view and also practical. Okay, t cube, cubic power, it's one-to-one, no problem there. And this is a linear function, it's one-to-one. So I am okay, but I have to think about it. Okay, let's move on. I have a formula, so I'm going to use it. I get an integral 2 times sine of cubic root of t cube. And I expect some major simplification at this moment. However, I still have to work because there is dx here. Okay, I differentiate on both sides and I get 3t squared dt is equal to 2 dx. And I'm interested in dx, so I'm going to move number 2 to the left. 3 over 2 t squared dt. That's the replacement formula I've been looking for. So I do the replacement. And incidentally, you can see why the number 2 was here. Because the guy who invented or who created this example wanted it to be nice here at this stage. Yeah, I did it like that. So 2 cancels. And let's make one more step. Okay, it's integral sine of t multiplied by t squared. And also there is number 3 here, dt. Okay. So the substitution went through and actually it was quite nice. If we used the direct substitution, we would get the same outcome, but it would take more work. That's the beauty of the mixed substitution. It saves you some work. You don't have to worry with roots, things like that. Okay, we have a new integral. Can we handle it? Good question. I don't know the answer. This is not in my dictionary. It's not a rational function, so integration using partial fractions is out. Substitution, I don't really see anything that I would like to hide. Integration by parts. Yeah, a polynomial multiplied by sine. That's integration by parts example. Let's try to do it with a chart. So f is the part which should be differentiated, which I want to disappear. And I definitely want to get rid of this polynomial. So that's my f. And g prime is the part which will be integrated, which will go up, which is sine of t. Okay, let's do the opposites. So I differentiate, I get 6t, and I take integral, which is minus cosine of t, and we can continue. Okay, so f times g is minus 3t squared cosine of t minus integral, and these two should be multiplied. So minus comes here, becomes plus 6t cosine t dt. Well, do I like it? No, but I like it better than this one. 1 power of t disappeared, which shows me that this is the right way. Let's try it again. Shouldn't forget, this part is already done. I have to carry with me until the very end. And this integral involves plus c, so I don't have to write it yet. Okay, I'm going to apply integration by parts here again. This part will be differentiated and this part will be integrated. I'll make a little remark for myself here. And if you are good, you can do it right away. So I take integral of cosine, which is sine, and this part stays the same. Then there will be minus integral, and I integrate it, so I copy it. And this part will be differentiated, which is just 6. Do I like this integral? Oh yes, I do. Finally, minus 3t squared cosine t plus 6t sine t minus 6, an integral of sine is minus cosine, so it's plus here, cosine t. And there is no integral in the formula which would be hiding c in it, so I have to write plus c. Am I done? No. Okay. I look at the question and there's no t in it. That's a clear giveaway that there is some work to be done. I have to do the back substitution. The answer must be given in the same language as the question. Okay. What's t? I can derive it from here. T is a cubic root, well, it's this formula. So, minus 3 cubic roots of 2x minus 4 to power 2 cosine of the cubic root 2x minus 4 plus 6 cubic roots of 2x minus 4 sine of cubic root of 2x minus 4 plus 6 times cosine. Could I put the cosines together to save some work? Not really. Okay. Cubic root 2x minus 4 plus c, comma. So that should be the answer, the formula. And now we have to inquire about validity. Okay. 2x minus 4 eats anything, cubic root also, sine also. Everybody's happy here. How about the answer? Yeah, everybody's happy. So x belonging to real numbers. There we go. Wow, what a beast. But we handled it. We are good. Okay. Was it really hard? Not quite. When you get some experience with substitution, you will sort of see that this is a good idea. If you want to talk about types, then one particular type that you can talk about is integral, in which you can see a square root or cubic root or simply some root of an expression. And then one good approach is to try such a mixed substitution. It may work, it may not, you never know, but it's a good chance that it will help you. Okay, let's have a look at another one. When we see an integral like that, we think of partial fractions. But first we have to prepare it for it. I copy the numerator, and now I try to break the denominator into a product of linear factors. If it's not possible, then I have to follow the path which tells me how to integrate with quadratic reducible factors. Well, let's see. Can I factor? Let's think about it. Yeah, it works. I see x minus 2 times x minus 1. So we got lucky actually. And now we can set up partial fractions. There will be 2 of them. So it's not much work. And here normally I would put a and b. But I will not do it now because we already know that there is a hiding trick and I can determine the values right away. I take number 2 and I substitute it here and I get 1 divided by 1, which is 1. And now I take number 1, substitute it here, and it's -1 over -1, which is 1 as well. So that's my partial fractions decomposition. And now here I can apply substitutions, just linear shifts, and I get logarithm of x minus 2 plus logarithm of x minus 1 plus c, and x is not supposed to be 1 or 2. And that's the answer. So it wasn't too bad. However, I said that sometimes there are exceptional cases when we have alternative to partial fraction decompositions. And this is exactly the case. When I look at this integral, I can notice that if I differentiate the denominator, I get exactly the expression which is next to dx. And this calls for substitution. Let's see. Let's say y is x squared minus 3x plus 2. Then dy is just 2x minus 3 multiplied by dx. Yeah, it's a perfect fit. We got so lucky. But sometimes it works. So we'll just finish the calculation. And we get logarithm x squared minus 3x plus 2 plus c. And then there's the condition. X is not 1 or 2. Is it the same answer? The answer is yes. If I take these two logarithms and I put them together, multiply out, I get exactly this. Is it easier? Yeah, I guess a little bit. But if I put a cubic polynomial here, then integration by parts will get really longer, while this will work exactly the same way, if we get lucky. Of course, what's the chance that the derivative of a polynomial here will appear over here? It's a small chance, but you never know. So it's definitely something worth thinking about. Now, I will use this opportunity to talk about another thing, which is definite integrals. Let's say that I want to integrate from 0 to 3 this function, 2x minus 3 over x squared minus 3x plus 2 dx. Well, the typical way is that we first find antiderivative. Okay, I will choose the second one because it's more compact. Logarithm x squared minus 3x plus 2. And we use it, substitute the limits. Okay, I take number 3, I put it here. 9 minus 9 plus 2, and I get logarithm of 2. Minus, I take 0, put it here, and I get logarithm of 2. And the answer is 0. Nice, no problem. However, I actually first had to evaluate the integral. So let's try it again, last time. 2x minus 3 over x squared minus 3x plus 2 dx. And now I apply substitution, just like before. Y is equal to x squared minus 3x plus 2. And I determine dy is 2x minus 3 times dx. And I get a new integral, dy over y. But now I can also change the limits, because this is a definite integral. And when I say 0, I actually mean that x is a 0. And this actually means that x is 3. And when we are doing substitution, all x's, even if they are hidden, have to change into y's. So x is equal to 3 or 0. And how do I change things? Using the basic substituting formula, which I chose. So using this formula, when x is 3, y becomes 2. And when x is 0, y becomes also 2. So that's how we do substitution with a definite integral. And then we could just finish the calculation. Here we actually got lucky. If you integrate from a to a, the outcome is 0, regardless of the function here. But yeah, this was a nice example which I made up to make it short. But if it didn't work like that, if there are two different numbers, we would just finish the calculations with y's. We wouldn't have to go back to x's anymore. And this can save you some work, namely this step. You wouldn't have to return to the original variable. It's important not to mix up variables. So the variable which is here should work with the variable which is here. Okay? And that's all concerning substitution. And that's all concerning the basic 3 methods. There is nothing more, essentially. Just these 3 methods and some tricks, a lot of tricks. So, of course, our forefathers, who didn't have computers, they had to be really good at integrating. They spent a lot of time thinking about it. And they collected examples of solved integrals into thick books. Really thick books. I have one at home. And they discovered many types of integrals for which they knew the right approach. So if you get really deeper into integration, one should really get a lot of practice, but also one needs to get familiar with some boxes. We saw a box for rational functions. We use integration by partial fractions. Or we have a box for integrals of polynomial times exponential. We use integration by parts. And there are many boxes like that. For instance, there is a box with integrals which are composed of sines and cosines. And there are some recommended substitutions, trigonometric substitutions. And many boxes like that. When I was a student, I learned about 10 of them. But nowadays, the number is smaller because computers are getting smarter and smarter. Sometimes perhaps even smarter than people. But fortunately not always, so there is still reason for us to be here in this world. Wonderful. Anyway, that's all for integration. And since I don't know how deeply you went into this integration, I'm not going to talk about the boxes anymore. Instead, I will do a bonus video where I will look at a really good example which shows all these methods in action. That's all for now.